I'll start. Here we are. Um, so this is our third to last lecture. Um, we're doing sequences of functions, and the whole point of this um, is that we're going to use these to study the exponential and trigonometric functions in our last two lectures. Okay, so last time we looked at the two notions of convergence. So we did pointwise and uniform convergence of sequences of functions. Okay, and now our question is, how do properties of the sequence carry over to their limit? So that's our question. If you've got a sequence of functions that converges in one of the two senses to a function f, well, how, I guess, do properties to the properties of fn carry over to f? And by properties, we're really talking, today we're talking about three. Continuity, integrability, and differentiability. Okay. So that's our setting for today. That's what we're going to talk about. For each of these three properties, we have a result. We're at least going to prove the first one because the proof is very cute. We may or may not prove the second one, and then the third one we're definitely not going to prove today in the lecture, but you can look in the book. Okay, so let's start with the bad news. The bad news is that if you have only pointwise convergence, then none of these properties carry over. Okay, so there are examples for all of them showing that just the fn's can all have that property and f doesn't have to. Okay, let's look at those examples. Example 1, let fn be x to the n, and let me just take its domain to be 0, 1. Okay, we looked at this last time. We saw that the sequence fn converges to f pointwise, where f is this function which is 0 unless x is equal to 1. Okay? Well, all the fn's are continuous. Each fn is continuous, but f is not. Okay. Remember, we had three questions: continuity, differentiability, integrability. So this shows that continuity doesn't carry over if all you have is pointwise convergence. Because continuity doesn't carry over, differentiability also doesn't necessarily carry over, because all of these functions are differentiable, but f is not differentiable. Because remember, if you're differentiable, then you have to be continuous. So each fn is differentiable, but again, f is not. Okay, so it's looking bad for pointwise convergence. One more example. we'll finish it off. Well, what we're going to show, we're going to come up with a sequence of functions where every one of the functions has the same integral, but the limit function has a different integral. Okay, so we're actually not gonna break integrability, but we're gonna break the integral itself. So, for example, 2. There. I hope my sharing's back. For example, 2. The actual formula for our function is not pretty, but the picture is pretty. So let me draw the picture. This is going to be a picture of Fn. Okay. Fn is linear from 0 to 1 over n. Goes up and then it goes down. So it's just making those 2 triangles. And then it's just going to be 0 all the way out to 1. Maybe I should make a different color. Okay. I want the integral to be 1. So what should the height of this triangle be? Any volunteers? N, yes. If we make the height n, then we'll get a triangle of area 1, and therefore our integral is going to be 1. These functions are clearly going to be integrable. You could use the fact that continuous functions are integrable to get that. Okay, so now let's actually define this function. If we wanted to go from 0 to n in value as x goes from 0 to 1 over n, that actually we want it to be n squared times x. Okay. Now, if we wanted to go from n to 0 as x goes from 1 over n to 2 over n, okay, I trust you could work this out. I'll just write down the answer. And there's the answer. N squared times 2 over n minus x. And then it's 0. Okay, so the function isn't very pretty, but the picture is pretty. And the reason we're doing this is to get our integrals to be 1. Now, I claim that this sequence converges pointwise. Okay, what does it converge to? So when you're thinking about pointwise convergence, you pick a point and you ask eventually what is the value of the function at this point.
Does it... Oh, were you going to say something here?
No, you go ahead.
I think it converges to the zero function.
Exactly. Yep. Because for any particular point, well, I guess I should say it this way: for any point that's not zero, eventually it's going to be over here, where the function is just defined to be zero. Um, and then actually all of the fn's are zero at zero, right? So for every single point, for every single value of x, eventually fn of x is going to be zero, and therefore the limit function is the zero function. Well, and so we have a problem. We have the limit, which then goes to infinity, of the integrals. That limit is equal to 1, because every single one of those integrals is equal to 1. But that's not equal to 0, which is the integral of the limit. Right? Because that limit is just 0. Okay, and that's why this section in the book is called Interchanges of Limits, because we're trying to move this limit. We're asking, can we move this limit inside the integral? And the answer we got here is no. Okay. Are there any questions on these examples before we go on to theorems?
I've got a question about uh, so if we're pointwise convergent overall, we can still have a subinterval that is uniform convergent. So would that mean we could split this integral up and then move the limit inside of some of the pieces? I don't know if that's useful, but that's sort of a thought that I was thinking.
Well, once we have our theorem, yeah.
Okay.
Yeah, sure. We'll have a theorem that says where you're uniformly convergent, everything actually works out well.
Okay.
Yeah.
So I have a question. So we say that it converges to the zero function. And intuitively, that kind of makes sense, but at the same time, I'm maybe struggling with like, I get that the triangle becomes like smaller and smaller in like its bottom, but like where does it? I was thinking that something would like shoot off to infinity at some point.
Yeah, it does, right? I mean, that's the whole thing. The height of the triangle is going off to infinity, and again, the integrals of all of these are equal to 1. Okay. Um, I would say what's happening here is that you have the correct intuition, which is that convergence of functions should be uniform convergence, right? So these functions are not converging uniformly to the zero function. They're converging pointwise to the zero function. And I guess what I'm trying to say is that probably none of us have good intuition for pointwise convergence of functions, because it does break those kind of things.
Okay, thanks.
Okay, we have a question in the chat. Let's see. Oh yeah, do we know that the limit function is integrable? Yeah, there are theorems about that, and we're not going to get into them. They're all a little bit complicated. Okay, so if we know our functions are integrable, do we know the limit function is integrable? There are extra hypotheses you can put on that will give that. I mean, okay, so I guess my answer to Madeleine's question is the answer is just no. If all you know is that your sequence converges pointwise, then you don't know that the limit function is integrable. Um, so we'll talk more about that when we get to that result, I think. Okay. So where are we? We started off by saying our question is what properties of Fn carry over to their limit, and we just looked at examples and we saw that if our convergence is pointwise, then our answer is none of the properties carry over. Okay. Now, obviously, I don't mean that they're guaranteed not to carry over. I just mean that there's no guarantee that they do carry over. Okay. Well, so this is why we define uniform convergence in the first place, because when we have uniform convergence, the answers work out much more nicely. Let's do our first theorem. We will do continuity first. So suppose you've got a sequence of functions and they're continuous. If the convergence is uniform, then your limit function is continuous as well. Okay. Any questions about the theorem before we prove it?
Yes, I have one question.
Mm-hmm.
So since we're dealing with the sequences, we only really care about the tail, right?
Mm-hmm.
So I don't know if that's really realistic to have some finite number of them are not continuous, but so we only care about the tail.
Right. So because we only care about the tail, we state our theorem this way, knowing that if an initial segment of these functions were not continuous, the theorem would still apply. We'd just throw away that initial segment. Does that answer your question? So I guess I'm saying it's just cleaner to know the fact that we can throw away an initial segment than to try and quote unquote strengthen the theorem.
Right. I guess it saves you from having to pick some natural number and have everything greater than to satisfy your condition.
Right.
Okay.
Yeah, you don't want that. You don't want extra variables in your theorem statements if you can avoid it. Okay. Now, this is great proof because it's just like a bread and butter advanced calculus proof. Let's look at the inequality we're going to come down to at the end. We're going to come down to looking. We're trying to prove continuity of f, right? So it's going to come down to evaluating the distance between f of x and f of c. Okay. Now we want to find some delta so that we can make this small. Okay. Well, how are we going to get any control over this? Okay. This is about the limit function we don't know anything about the limit function, but we do know that the limit function is, the things are converging to the limit function. So what we could do is we could do I guess I would call this a double triangle inequality. Okay. Let me do it this way. I would like to compare f of x to fn of x. Okay, but to do that I need to add in an fn of x. Okay, so, I'm adding 0. It's a standard trick. Now, so I've taken care of the f of x. I would also like to compare the f of c to an fn of c. That one is negative, so I want to add an fn of c. Okay, but I want to add 0, so I'm going to also subtract an fn of c. Okay, so this is a true statement. And you can see I've taken care of the f of x. So I'm thinking I want to compare f of x to fn of x. And I want to compare f of c to fn of c. And now look at what's left over. That's a difference between fn of x and fn of c. Well, okay, so now I'm going to be able to make the first of these small because of the uniform convergence. I'm going to be able to make the second one, this fn of x and fn of c, small because the fn's are continuous. And we're going to be able to make the comparison between f of c and fn of c small, again because of uniform convergence. Okay, so what would our triangle inequality here would be that we'd say this is less than or equal to f of x minus fn of x plus fn of x minus fn of c plus, and now I will put a negative in here, and I will get, I will get f of c minus fn of c. Okay. And so we're going to have these three quantities. We want to make them all small. I'll highlight in green what's going to be small by uniform convergence, and in yellow what's going to be small by continuity of the fn's. Okay, so that's the game plan. Now let's write the proof. Are there any questions before we go writing the proof?
Yeah, how do we know the yellow one is small?
By the continuity of the fn's.
Mm-hmm. Gotcha.
So, yeah, so the thing I really like about this proof is that the quantity we want to approximate has no fn's in it at all. So we introduce those because we want to actually have those in there. Okay, so let's see if we can do this. Let's let epsilon be given. Now, let's work first on the green ones. we want to get the difference between f and fn at a given point to be small. So because the sequence fn converges to f uniformly, there is capital N in the natural numbers. Let's make a little room here. Such that f of x minus fn of x is less than, now, we are eventually going to want the sum of,
Dr. Bader,
yeah,
don't we need n greater than or equal to capital N?
yeah, I'll be writing that as soon as I'm done.
Oh, okay.
I'm going to fill in how close we want these two things to be first. Okay, so eventually we're going to want the sum of three things to be less than epsilon, right? And since there's three things, let's make them all less than epsilon over 3. Okay, so I'm going to want to make the difference between f and fn less than, and I said 3 and I wrote 2. Let me try it again. Less than epsilon over 3. Okay. And what is this? For all x in A and n in, and n greater than or equal to capital N. Therefore, for all x and c in A, we have, and now we can put this in. We won't get quite the conclusion I promised. What will we get? We'll get less than, the two quantities circled in green will each give us an epsilon over 3. So we'll get a 2 epsilon over 3 plus that third quantity. Okay? Now, what I've written isn't quite correct, because I need to say for little n at least capital N in there, right? Okay, there's a cute little trick that we can do to avoid saying that. Since this stuff is true for all little n at least capital N, let's just put capital N in as our subscript. Ah. So I'm going to change all these f of little n's to f of capital N. I just have to remember where they are. Yeah, it would have been easier just to write over them. Okay. And I will erase this comment about little n. Okay, I hope everybody's clear about what we did there. We just said since we're getting the bounds we want for all little n at least capital N, we'll just use capital N as our subscript. Okay. Any questions before we go on and finish the proof? No?
So in the circled thing, there should also be in the circled in yellow, there should also be capital N's.
No. No.
No.
Yes. I'm sorry, yes. Very much so. Sorry. You're right. The circled in yellow became that, and the circled in green became that. Yep.
So
Should
then
the second green circle not have the N for
Ah,
this?
I did such a bad job. Okay. Yes. There we go. Better?
yes.
Yeah, finally correct. Yes, I guess you can just check. On the first line we have 4 capital N's, so on the second line we should have 4 capital N's, and then 2 of them leave us, and we're left with 2. Okay. Ooh. Okay, now that we got that inequality, we are almost done. Now, we haven't used the continuity of f sub capital N. Well, we're just going to use that continuity in order to say there exists a delta, and that's going to be the delta that we wanted in the first place. Right, so because f sub capital N is continuous, there is a delta such that, and I would like this quantity to also be less than epsilon over 3. And if I make that less than epsilon over 3, then you can see the whole thing is less than epsilon. So therefore, f of x minus f of c is less than epsilon whenever x and c are within delta, and that's what we wanted to prove. Okay. Any questions? Any more questions? Any more mistakes that you've spotted? Right, so Madeline asks, what would happen if we didn't have uniform convergence? Yeah, so if we don't have uniform convergence, our issue is that for every different, or let's look at where we used uniform convergence. We used it here. There is an n such that f minus fn is less than epsilon over 3 for all x. Okay. So without uniform convergence, we get a different capital N for every x. So our capital N, okay, and so when we actually applied this, we applied it to x and to c. So let's see. the capital N for that X would not necessarily be the same capital N for that C. And you might say, okay, that's fine. We just get two values of capital N, just take the maximum. Except this proof has to be valid for all X and C. So then we end up taking the maximum of all the capital N's for every single point. And if our convergence is only pointwise and is not uniform, then we're just going to end up saying, you know, it'll just, there won't be a maximum of all those capital N's. That makes sense?
Why won't there be a maximum? Is it just, it's unbounded?
Yeah, I mean, so for one X, that capital N will be 10. For another one, it'll be 200. For another one, it'll be 1,000,000. You know, and it'll just keep going like that.
And if they were bounded, then there's some roundabout way that it would be uniform convergence?
Precisely. Yeah. That's
Okay.
equivalent to saying that they converge uniformly.
Okay.
In fact, that's the definition of. If that's true for every epsilon, that's the definition of uniform convergence, just in a slightly restated way. Okay. So
Just to clarify, the way that proof would break down is that we couldn't take a maximum of all of the n's. That's where it would break.
Yeah, well, it would first break because you'd get different n's. You'd get different capital N's, but the proof needs the same capital N.
So it would break in this yellow circle. These two n's would be different, so we can't compare them.
Right, and so then you try and fix that by saying, well, I'll take the maximum of the two values I get.
Mm-hmm.
But then it would break because you need to prove this for all points, and so you would really need to take
Okay.
the maximum over all points of all the capital N's you get.
Okay.
And then it would break because that maximum does not exist.
Okay. Because if it did, then we would have uniform convergence.
Exactly.
Gotcha.
Yeah. Yeah. None of what I'm saying is true. You have to sit down and think about it, but that's all true. Okay. So the big takeaway from the theorem: if you have uniform convergence, continuity of the sequence implies continuity of the limit. Okay, we're going to use this on Friday and again on Monday. On Friday, we're going to use it just to say that the exponential function is continuous because we will express the exponential as a limit of continuous functions. Okay. Now, two more theorems to do. Clearly, I'm just going to state them because we are running short on time. So the next theorem I want to state is integrability. Suppose you've got a sequence of integrable functions. If that sequence converges uniformly to F, then F is also Riemann integrable. Okay. I guess there's, you've seen the last theorem. This is just like the last theorem. Same hypothesis, same kind of conclusion. Integrability carries through. We don't have time to do the full proof, but we have time to maybe show you kind of what's going on. And again, so the idea is that we use a sort of Cauchy condition on the sequence. So we say there exists a capital N such that for M and N, at least capital N, we have this for all X in our domain. And our domain in this case is a closed interval because that's where we're concerned about. Okay? So again, this is essentially a Cauchy condition. You can get this Cauchy condition by comparing both the Fm and the Fn to F. Right, you make, really this is the, one way to do this would be, this is the capital N for epsilon over 2, if that makes any sense. If you make Fn within epsilon over 2 of F for all X, and then you take M and N, at least that capital N, then they'll both be within, for every value of X, they'll both be within epsilon over 2 of F, so they'll be within epsilon of each other. Okay? And now, by theorems about integration, you are allowed to integrate this inequality although, once again, the strict inequalities turn into weak inequalities when you integrate. Do they?
Is that a theorem we covered, or is that in the book?
Mm-hmm. Is this theorem? This theorem is in the book. Gosh, is it a theorem we covered? It is.
Isn't this just like the homework problem? Or similar to it?
It's very similar. I think we did do this. Oh no, okay. I think we skipped this, but this is theorem 7.1.5. Okay, and what that theorem says is that if f is less than or equal to g at all points, then the integral of f is less than or equal to the integral of g. Okay, and that's actually a really easy theorem to prove because it's true for every one of the Riemann sums. And therefore it's true for the integral. Your homework problem is actually harder than this because your homework problem has that absolute value, so you have to get a little bit more. You have to dig in a little bit deeper than proving this theorem.
Thanks.
And okay, so therefore, like this integral is actually converging to 0. And you use this to get some control. You end up looking, this is the start of the proof. Then you end up looking at Riemann sums between f and fn. Okay. Anyway, that's some ingredients of the proof given to you in a slightly random order. Now, I promised you one more theorem, which is about differentiability. Differentiability, I guess the big high level takeaway is differentiability is a pain. It does not carry over well at all. So here is a theorem. Let Fn be a sequence of functions from, we'll just let our domain be a bounded interval. Okay. If we take a point in that bounded interval, and let's see, we would like the sequence of functions to pointwise converge there. So what does that mean? The sequence of function values is converging at that x naught. And we want all of the derivatives of the f to converge. Uniformly. And we'll call the function that converge to g. We can't call it f prime because we don't really, well, that would be saying that it's the derivative. So let's see. I was writing this as an if statement, but it really needs to be a suppose because we're going to start a new sentence and we haven't said what's true. So the sequence of we converge at this point, our derivatives exist and they converge uniformly to some function g. Then the sequence we started with actually converges uniformly. To a function f, which we might as well say is defined on the same interval. That is differentiable. And okay. So the big takeaway from this theorem, which I realize we're out of time now, but the takeaway from this theorem is that if you want if you want to get differentiability, you need not the sequence of functions to converge uniformly, but the sequence of derivatives to converge uniformly. Okay, those are the key words of this theorem. Okay. And of the three theorems, this is by far the most difficult proof. I guess you can kind of see from the statement that we've got a lot of moving pieces. Okay, so let me end there. Those are the three properties, the three theorems about carrying over. None of them work for pointwise convergence, and all of them work for uniform convergence given certain hypotheses in the differentiability case. Okay, so I will